Hey guys, Mr. Wemp here. We're going to look at the final installment of our Mechanical Advantage series, and we're going to be looking at gears. We're going to be looking at simple gears and complex gears, but let's start out with some basics about gears. There's a couple things that you need to know about gears. First of all, we know that there's an input, so this would be like you cranking on this gear. And then there's an output gear. So there's always an input and an output, and it's important to distinguish between those two. So this is turning, and this is being turned. I don't know if I spelled that right or not. But turning and being turned. And then we have something in here in the middle called an idler, or an idle pulley. Or excuse me, idle gear. And all this does is change the direction of the gear. It doesn't matter what size it is, it's going to be the same. So if this is a 1-inch diameter and this is a 1-inch diameter, this one's 0.25, it won't make any bit of difference. All we have is we've got this guy rotating this way, we've got this guy rotating that way, and because this rotates, they always rotate opposite of each other, and so then this one will rotate that way, giving us a gear that turns, the whole system will turn clockwise. Now keep in mind that they turn separately. If I want this one to turn the same direction as this one, I have to put an idle gear in there so that they all turn the same direction. Okay, so we have the input here, we have an output here. Okay, input and output. Now there are some variables that we can look at to find out gear ratios or the mechanical advantage. The mechanical advantage and the gear ratio are basically the same thing. So variables that we need to know the letter N. Letter N is equal to the number of teeth that a gear has. We need to know the diameter of the gear. Okay. Well, we don't need to necessarily know that, but we need to know that that is what D is. Then we've got this guy here, which is kind of a funky looking W. I don't remember the Greek symbol that is, but it's kind of a funny looking W. That is angular velocity, which is a fancy word for speed. Okay, and that could mean revolutions per minute, PM. Okay, so it could mean both of those. And then we also have the letter T, which is equal to torque. Okay, so if we know the torque going in and the torque going out, we can figure out a gear ratio. Okay, so we use some subscripts. In the example that I have here, I've got some different things. So we might know the number of teeth in the input gear right here might be 6, so N is equal to 6. And the number of teeth in the output gear right here might be 12. Okay, I know that if this is 20 RPMs and this is 40 RPMs, this one's spinning 40 times per minute. This is twice the size as this one, so then it has to turn half as fast. I also know that if there's 6 teeth on this one, since this is twice as big, it'll have twice as many teeth, so it'll have 12 teeth. I also know that by measuring it, if this is 2 inches in diameter, then this one is 4 inches in diameter. Now I'm still 2 to 1. Okay, so we have all those different things. So how do we solve these? Well, there's some equations that we want to look at to find the gear ratio. And first of all, GR is the gear ratio, and GR is equal to mechanical advantage. Now there's not going to be an IMA and an AMA here because well, you can't really change how many times it turns. It's going to turn how many times it turns. Okay, so if we put all these into a fraction, we end up with something that looks like this. The gear ratio over 1, it's a single number, is equal to number of teeth on the output over the number of teeth on the input, which is also equal to the diameter of the output over the diameter of the input, which is equal to torque of the output over the torque of the input, and it's also equal to, now you got to be careful on this one because this one's backwards, it's equal to the angular velocity of the input over the angular velocity of the output. So let's see. Let's put a fancy little, let's put a star right there. Okay. So this guy, we're going to mark it here as backwards. Now it's important to remember that, because if you do it the other way around, well, obviously you'll get something completely different. Okay, so all of these are all the same things you can do to find the gear ratio. So if you know the number of teeth on the output gear and you know the number of teeth in the input gear, you can figure out what the gear ratio is. Okay, it's all the same thing. So that's with a nice simple gear train right there. Okay, let's take a look at one that's a little bit more complicated. It's still a simple gear train. So we'll build it and we'll set it up here. Basically, we've got, let's see, a big gear. Let's see, a not so big gear, a little tiny gear, and another big gear right there. And let's move these guys around where they belong. We've got one there, and one right there. Okay, so this looks pretty straightforward. We have gear A, and it is a 20 tooth. We have gear B, and it is a 12 tooth. Okay, don't know, that's not torque, it's the number of teeth on the gear. They usually measure like that. We have gear C. Gear C is a 5 tooth. And then we have gear D, which is a 20 tooth. Okay, so we've got 4 different gears. So four gears. Now, my first question is, what is the gear ratio between gears A and B? Okay, so the gear ratio of A and B, we have the number of teeth out. Oh yeah, we didn't figure out which one was driven. So which one of these is driven? Well, let's see. We'll say that this is our input, and ultimately this is our output. So we're going this way. It's going to go here. So we'll have this one. Comes this way. So we'll have there. And we'll end up with that, which means that it's going the opposite way again. So our output will be here, our input will be here. So we have to choose one. Okay, so I'm turning this guy with my hand, it's turning out here. Okay, so my input, the gear ratio of my input, I know that the number of teeth out over the number of teeth in is equal to the gear ratio over 1. Okay, and what do I get here? Well, I've got, we're looking at A to B, right? Gears A to B. My input is 20, and my output is 12. So 12 divided by 20 is equal to 0.6. Okay, 0.6 over 1 is my gear ratio for A to B. Okay, what if we look at B to C? Well, we have the same thing. Number of teeth. We look at the input here, it's because the whole thing's going this way. So we have 12 over 5. Okay, we have output over input. The output's 5 over 12. And that is 0.42 over 1. And then finally C to D, we end up with, what do we have? We have 20 over 5. Remember, we're doing output over input, so we're doing C to D. The output is 20 over the input of 5, and that is 4 to 1, or 4 over 1, excuse me. So if I add these three together, guess what I get? So I get 0.6 over 1 plus 0.42 over 1 plus, where'd it go? 4 over 1. And what do we get? Oh, excuse me, not plus. Okay, so here's something, we're going to take a little sidebar here for a second. When I take my mechanical advantage of different machines, I'm going to multiply each machine. So this one and this one would be multiplied with this one and this one, and that would be multiplied with that one and that one. So if I multiply these all out, sorry, I had pluses there, but if you multiply them, I end up with 1 over 1. Okay, so that pretty much gets rid of all these. You'll see that it all adds up to 1 over 1. But I could have also done another trick with this, and that little trick would be to completely ignore, let's see, because we're in a simple gear train, everything in between the input and the output is totally irrelevant. So if I completely ignore all of these, then I can do that. And you can see that my input is 20, my output is 20, so 20 over 20 is the same as 1 over 1, so my gear ratio is 1. If I turn this thing one time, it's going to turn one time over here. Okay. If I had a different gear ratio, it'd be a little different, but because it's a simple gear train, everything's all lined up, I can just cross these out. Okay. Now that's a nice simple gear train. We get into something a little more complicated if we do a compound gear train. So let's do a compound gears. Okay, now compound gears are basically the same thing as a gear train. We've got a large gear and a small gear, and then we also have another large gear, and I'm going to get these sorted out a little bit, and another small gear. So let's get these organized where they need to be. That one can be wherever. That one goes there, and then this guy goes right here. And let's see, let's fill that guy there, and whoops, undo that. We'll just leave it like that because that'll work. So basically this gear right here is in front of the other gears. Actually, let's just undo it all together. So this gear right here is in front, so this is gear, let's see, we'll call this gear A to B. Okay, these two turn together. These two share an axle. So when B turns one time, C will turn one time. Doesn't matter how big they are because they share the same axle. This is compound gears. So A and B are connected. So A and B are one gear train. And then C and D are another gear train. So C and D are another gear train. Now D doesn't have anything to do with B other than the fact that B and C turn together. Okay, so if we've got this guy at 10 teeth and this one is at 40 teeth, C is at 20 teeth and D is at 50 teeth. Now before we could cross out these middle ones, but the problem here is we've got two simple gear trains that work together. Okay, so we're going to be looking at something a little bit different. So gear ratio, we're going to look at the gear ratio of C and D, and we have the number of teeth out over number of teeth in, and we have let's see, where's our input here? Looks like this is our input and everything's going that way, so that makes this an output. Okay, so D is our output, so we have 50 over 20. Okay, and that gives us 2.5 over 1 for our gear ratio of C and D. Okay, then I need to look at A and B. So let's go over here to gear ratio of A and B, and again we have number of teeth out over the number of teeth in, and number of teeth in is 10 and number of teeth out is 40. 40 divided by 10 is 4 over 1. Okay, so now we've got these two right here. Now this is a compound machine, so what are we going to do? We're going to multiply them together. So we take 2.5 over 1 times 4 over 1, and that gives us 10 over 1. Okay, and so our gear ratio is also our mechanical advantage. So you can see by multiplying this simple gear train and this simple gear train together, we've gotten a 10-to-1 ratio. Now I could do the same thing with a simple gear train here, but I'm going to end up taking up a lot more space. The gears have to be a lot bigger. So you can see, to get this guy right here, I got myself a gear ratio which spun this guy faster, right? And then because this is spinning a little bit different than here, we end up compounding our gear ratios to make this nice 10-to-1 And it takes up a lot less space. If I were to spread these out across the page, it would fill up the whole page. Okay, so that's pretty much it for compound gears and simple gears. You'll find that pulleys and belts and chains and sprockets are pretty much exactly the same thing. They're just gears that are connected by a string instead of teeth. Okay, so be prepared to answer some questions at the end of the video on gear ratios and different examples, and then be prepared in class to run this in a lab. Okay, we'll see you next time.